Hi, I'm Heather James, Conference Producer for Technology Networks, and I'm here to introduce our final talk of the day, Material Supply Considerations for Lithium-Ion Batteries. I am pleased to welcome Dr. Linda Gaines. Dr. Gaines is a Transportation Systems Analyst in the Energy System and Infrastructure Analysis Division at Argonne National Laboratory. She studied for her BA in Chemistry and Physics at Harvard before obtaining a PhD in Physics from Columbia. With a heavy focus on problem solving applied to efficient resource use, her most recent work has investigated the recycling of lithium-ion batteries to reduce transport impacts. A notable voice in the industry, she is also an editor for Sustainable Materials and Technologies and on the editorial board for Scientific Reports. A warm welcome to you, Dr. Gaines. Following the presentation, we will also have a Q&A session, and we welcome any questions that you may have. Please ask questions using the Q&A system to the right-hand side of the video player. I will now hand over to Dr. Gaines to begin her presentation.
Thank you so much for inviting me. So my presentation has to do not so much with the electric vehicles themselves or overall energy issues. It has to do with the batteries themselves and the materials that make them. The work I do is part of a much larger group at Argonne. We're concerned in large part with life cycle analysis, but also with material issues in general. And recently there's been an added concern based on the Biden administration's concerns, specifically with equity issues within the supply chain. There'll be a few slides that mention that. The main product of this group is called the GREET model, which is used by thousands of people around the world, and it enables you to compare different technologies and different technology use paths to understand what the environmental impacts will be for that. And so I just wanted to start with that as background. So life cycle analysis is a very important tool that has been recognized much more recently than it had been in the past. The idea is that you need to understand when you're using a product what all of the impacts are, starting from materials in the ground all the way through the production and use and end-of-life treatment of the product. So this is a life cycle analysis for battery cells for an electric vehicle. And what it shows is various important impact categories, from the total energy used to make the battery all the way through the environmental emissions of making it as well, and the water used. And what I glean from looking at this chart is basically by looking at the colors, and the first thing that grabs you is the blue, which is the cathode material. And so that tells you that the cathode material is really important from the standpoint of the energy use and the material inputs. And it turns out that it's also the most important part of the battery as far as the economics. The other thing that jumps out at me that most people don't pay much attention to, which is the aluminum. And what you can see is that aluminum production and use is pretty energy intensive. And so we should pay a lot more attention to what happens to the aluminum and whether we can reuse it. And we'll get back to that. So that was just for producing the material for the battery. This chart is the life cycle analysis for the entire electric vehicle's life cycle. On the far left, you can see what the total energy use is. And in this particular case, it's actually greenhouse gases, but greenhouse gases go right along with the energy use. If you have an internal combustion engine vehicle on the far left, there's a large amount of carbon dioxide and other greenhouse gases emitted over the course of the life cycle. Most of that is from the use phase. It's from burning the fossil fuels. So the next two bars are two different chemistries of cathode for electric vehicles. And what you can see is the total greenhouse gas emissions over the life cycle of the vehicle are way less, in spite of the fact that the production impacts from the battery and the vehicle at the bottom, the two blue bars, are somewhat higher. So what that means is that basically there's a payback period. And if you just make an electric vehicle and then don't bother to drive it, the impact per mile is way more than that for an internal combustion engine vehicle. But once you start driving the vehicle for 10 or 20,000 miles, you pay back that deficit, and the life cycle emissions and other and energy use, etc., are much less for the electric vehicle. On the right is sulfur dioxide emissions, which for an electric vehicle can be fairly large compared to an ICE, but that's because the ICE has now gone to essentially zero emission sulfur emission fuels. And in fact, these sulfur emissions are, first of all, small on an absolute basis, and second of all, do not occur for recycled battery materials, because the impacts are from treating high sulfur ores that the cobalt and the nickel are extracted from in many cases. If you look at the impacts all across the battery life cycle, what you can see when you do it quantitatively is that anything you can do to reuse the battery or the material has lower impacts than things that require you to dig up new materials from the ground. And in fact, we did a comparison of virgin material production to production of battery materials from recycled materials. And what you can see with comparison of new materials to three different recycling technologies is that direct recycling, which is what I'll talk about a little bit more in a minute, the direct recycling has much lower impact in all of these categories than does producing material from scratch. Now, there's been a lot of talk about a circular economy, and the idea is really good. The idea is once you dig up material from the ground and put it in a product, you can recover the energy and the materials themselves from the product and reuse this material over and over in a circle, and you don't need to extract any new materials from the ground. And that's a really good idea. It gets people thinking about conservation and recognizing that growth is not sustainable on a finite planet. But there are some practical problems with that. And the first is that battery use is growing very rapidly. And so what that means is that the material we're getting back from use from, let's say, 10 years ago is not nearly enough to satisfy our current demand. So you can't be circular until growth stops. And I have some charts later, I think, that will illustrate that. The other thing is that if technology changes, the material you're getting back may not be what you actually need at the current time. The other interesting question that the circular economy studies raise is how best to evaluate technologies. They've come up with a measure called circularity that has lots of parameters in it, but it depends drastically on people's personal opinions of what's more important than other things. And it will depend on your location and basically your point of view, your economic point of view, and where you are geographically. Energy use is not the only important thing. Jobs are something you can also measure. Resource depletion, greenhouse gases. That's an open question. So I think it's important to look at various measures when you're doing a study. So what's the problem we're dealing with here? Well, basically, we got to looking at electric vehicles because we were so dependent on oil and we were worried about greenhouse gases. So we've pretty much eliminated the problem of oil imports, but we've gotten ourselves into another bind, and that is we're short of these critical materials for the batteries. I saw a recent panel discussion where several experts were being polled as their opinions of whether we could actually get the materials that we were projected to need. And all of the experts thought that the current projections were really improbable. We were not really going to be able to get those materials. And that is also corroborated by the Liebridge report that came out last year by an industry and government panel that studied these critical materials. There were also two important reports that the Biden administration produced when it first came into office. And the basic results of those was a recognition that the United States was somewhat short on capabilities in several of the steps of the battery supply chain. In particular, we don't have the raw materials. We don't have the production capacity to refine those raw materials. And our capacity on the recycling side was at that point somewhat deficient as well. This slide just makes the point about raw materials. The critical raw materials for cathodes for the batteries are cobalt, nickel, and lithium. And what you can see from this is the United States produces about 10 million vehicles, automobiles per year. If we took all of the US reserves, according to the USGS, of cobalt and nickel and put them into the supply of batteries for 1 year's supply of cars, if they were all electric, and we wouldn't even have enough material to make those 10 million cars if they were electric. So we're kind of stuck with imports. We're in a better position with lithium. And there have been some recent discoveries that imply that the US could be quite self-sufficient in lithium, at least for a while. And now this slide gives you a picture of how the battery materials move around the globe. The materials are sourced from around the world. In particular, the lithium is sourced from Chile and Australia. The cobalt comes from Congo. The nickel comes from Indonesia and Australia. But we don't get them directly from these countries. They're refined in China. China also makes a lot of the cathode material, as does Japan. We then import those materials. So we are quite dependent on material that's been transported a long distance through countries of concern. And this is a significant uncertainty for US national security and for economic stability. So that is a real issue. And one step worse than that is that, in fact, our recycling capacity at this point does not include producing the cathode materials. And so even if we recover the basic materials in the United States, they will then be shipped overseas to be made into cathode material and then shipped again. So we end up importing the same material yet again. And that takes a lot of energy. It makes emissions. It's just generally not a great situation. Luckily, the US recycling capacity is getting built up at this point. Now, you may wonder why I have a picture of an apple tree. This actually replaces a cartoon that I don't have the permission to use, and our copyright folks are very concerned about that. And what this basically is pointing out is that people on one side of the fence here are getting to use these apples, these resources that are produced elsewhere. And the equity concern there is that the source of these raw materials may not be actually adequately compensated. There may be environmental impacts and human rights violations in these countries that that are not being addressed by the users. And this is just a paragraph that I'm proud of that we got put into one of those reports to the Biden administration. And what it basically says is that if you don't have the cathode production facilities within your in the US, we'll need to actually export the recycled materials and then import them again. So that was a concern that we raised that hopefully is being addressed at this point. Although right now, still most of the recycling capacity in the world is not in the US or in Europe, it's in China. This slide just emphasizes the environmental justice issues having to do with making battery materials. There are environmental impacts and also positive environmental impacts in some places of extracting these materials, and these issues are not always properly addressed. And I've included this Sankey diagram of cell production and vehicle production to show that the United States does in fact have significant capacity in those legs of the supply chain. What is wrong with global supply chains? Well, I think it should be fairly obvious that if you're shipping material all around the globe, you can get anything you want, but there are possible disruptions. We had major problems during the pandemic. There are still some supply issues that are going on, and there are impacts from the transportation, and they may not all be equitable. So how can we fix this? How can we actually get all that material back and use it in the United States? Well, there's one issue that our free market that enables lots and lots of battery designs based on different module designs, based on different cell designs enables. And that is there's a huge variety of stuff that's going to be coming back for recycling. The more variety there is, the more different ways you have to be able to treat it and separate the different parts. So there's good news and bad news about all different varieties of batteries being available. You can get a battery that does anything you want, but then maybe there are potential issues at the back end of the supply chain. So one could think about designing for recycling. Some uniformity and standardization would help with the possibility of robotic disassembly, because disassembling an EV battery pack is incredibly labor intensive right now. And that means it's very costly. And that certainly hinders getting material back for reusing the material. There are lots of different technologies that are being considered that would enable easier disassembly. Manufacturers of vehicles are extremely leery of considering these because they want to make their main concern is safety. And they are concerned that changes in the battery design could impact safety. I think this is a soluble problem, but it needs to be addressed at the cell level. And this is my tribute to some buddies in Great Britain who came out with this statement. We don't actually have Victoria's sponge cakes much in the US, but the idea is that when batteries are recycled at this point, the first thing that happens is usually that they're shredded and all of the pieces are mixed up. And the main task of the recycling processes is then to separate everything back out. And so the idea is that if you could separate stuff before you mix it all up, it would make recovering individual products much, much easier. This is our Argonne and DOE basic recycling chart. And what it shows you is that on the blue line, it shows how one makes a battery, starting with materials in the ground. You refine the materials and make them into battery materials, put them into a battery, use them, and then it comes to what you do at the end of the battery's life. Well, first of all, you can use it again, and that is a very interesting topic that's being discussed and implemented across the world, and that enables you to get more bang for the buck on every pound of material that you use. If you can't reuse the battery and you need to recycle it, you can just throw it in a furnace and get back to essentially really good ore and start over. Or you can chop it up and dissolve it in acid and get back to basic chemicals that you, again, can react together and put into making new cathode material for the batteries. Or what I think makes a lot more sense is direct recycling, where you actually can keep the battery crystal and materials intact and reuse them without having to reconstruct the complicated crystal structure. I've also put scrap on this chart. It's very important right now because there aren't a lot of electric vehicle batteries coming back yet. In fact, they've been lasting really well, and so they're still in service. So if you're trying to build up a recycling industry, you need to have some feedstock. And luckily, or maybe not so luckily, battery manufacturing at this point produces a lot of scrap material. And that scrap material is excellent feedstock for these new recycling plants. And so the fact that there is scrap is really in a way, good news. So this slide is about the high temperature recycling process, which gets you back basically the copper and the cobalt and the nickel out of the batteries, but the aluminum and the lithium are lost to the slag. The lithium can be leached out of the slag, but that's only happens when the lithium price is high, which currently this week it's down. So that's not economical at this time. The other thing that's lost here is all of the organic materials. The carbon in the cathode material, the carbon in the anode material is burned, as are the plastics in the separator and the organic solvents in the electrolyte. So all of those organics are essentially burned as fuel for the process. So those all need to be made again, and if you want to have a new recycled battery. A somewhat less crude process is the hydrometallurgy, where everything is dissolved in acid, and the aluminum and copper can be recovered before everything is dissolved in acid. And these processes are currently commercial in several places in the world, including a couple of places that are just getting started in the US. But direct recycling has a number of advantages. One is it doesn't break everything up into its teeniest bits, and so it recovers a lot of the processing energy. It can be used now for manufacturing scrap, which means that you don't need to do a very complicated recycling process. It's low temperature, low energy, and so it's got lower impacts overall, as was shown in the graph earlier. But it has not yet been demonstrated fully on an industrial scale. There are some plants in the US that are currently being built to demonstrate that. So stay tuned on that. And this just gives you an idea of why we think direct recycling looks so much better. And instead of breaking material down into its simplest building blocks, we can actually recover the complicated layered structure from the cathode. And so it should be obvious that that enables you to do that in a somewhat lower energy, lower impact way. That also has some economic advantages because some of the new cathode materials, like lithium iron phosphate, are built from lower cost metals than the original nickel manganese cobalt cathode materials. And if you can just recover the value of the elements and the cathode material is made from less valuable elements, then your recycling process is going to be less profitable. But if you can actually recover the most valuable part of the battery, which is the cathode material, then you're likely to have a more economical plant. So, is recycling the answer here? Well, unfortunately, no. The problem here is rapid growth. What you can see on the right is the growth of lithium-ion batteries in the United States market. The biggest chunk of those is the yellow, which is light electric vehicles. The blue on the top is the portable electronics, which up until recently were the main use of the batteries, but the electric vehicles have taken over by now. And the point of this is if you could recover everything from, let's say, 10 years ago, which is in fact less than one battery lifetime, you could still only supply under 10% of current demand with that material. So recycling at this time is just, it's a good thing, and we need to get that material back, but we still need other virgin raw materials. So on the left is sort of a conceptual idea of how recycling, the red line, which is just the demand curve lagged by 10 years, enables you to catch up. If you could recover all of the material that you were using 10 years ago, you would eventually, if demand flattened out, be enabled to get all of your demand supplied from recycled material. But that doesn't happen until the demand curve flattens out. On the right is actual US data with the amount of battery material placed on the market on the top curve, and the amount of battery materials that could conceivably be gotten back from recycled material on the bottom curve. The demand hasn't flattened out yet, so we're still way behind. So one question that comes up very often is what percent of the batteries are actually recovered. That previous graph was assuming you could get everything back and none of it got exported, which is another issue. When I was showing the world map earlier, I did mention that recycled materials were getting exported, but there are also used batteries and used vehicles being exported. So the US and similarly Europe are losing material. We import these critical materials and then we export them again at some later date, so we have to keep importing. But Circular Energy Storage in London has been compiling recycling statistics to the extent possible for quite a while now. And the basic conclusion is that a lot of the battery material is in fact getting back to recycled. Approximately half of the material from the US does get recycled, but it's recycled mostly in China. So if we don't have the materials in-house, and we're not going to get it back from recycling, maybe we need to think about other materials. What else can we use to make these battery cathodes? Well, luckily, there are lots and lots of different cathode chemistries that are being experimented with and, in fact, put into commercial production at this time. Here's a list of some of them. Many of these are available domestically or from countries that are not considered countries of concern. And I'll just go through these very quickly. Lithium iron phosphate is getting to be a big deal in the US and in Europe as well. There are plants planned in the US. There are mines being dug for phosphorus materials in Quebec. The US does have phosphate rock. We have chemical phosphoric acid capacity in place. There's plenty of supply of iron, and we do have lithium, so we could actually consider having a domestic cathode supply chain within the US. This graph is just to give you an idea of how much iron ore and what the different scale of the different metals is. It's somewhat of an exaggeration because it's iron ore and refined other things, but we're not running out of iron. Manganese is another material that's being used in some of the cathode materials. The US does have reserves of manganese, but it's not particularly rich ore, and so we are currently importing from Africa. But these are not countries of concern, and so manganese is a high supply material that we could be using for cathodes more than we already are. You've heard of sodium-ion batteries. There were, just within the last week or two, there were announcements of companies that are actually producing electric vehicles using sodium-ion batteries. We certainly have enough sodium and could get an essentially unlimited supply from seawater. So that's another way that we can relieve some of our material supply constraints. You've probably heard of lithium sulfur batteries, which are not commercial yet, but do offer some promise perhaps. We don't need to worry about sulfur supply. Sulfur is essentially a waste product. And we've also been talking about lithium air batteries, and we have lots of air. Another kind of battery that could be more efficient and therefore reduce the total amount of materials that we needed is solid state batteries, which instead of using lithium ions, although they do use lithium ions in the cathode, use lithium metal in the anode. And the US is a significant part of the lithium metal production capacity of the world at this point. We're not way behind yet. So this is another place where we could manage to be our own supplier, and we're not behind the curve yet. If we were to be making large quantities of lithium metal, it would make a lot of sense to develop a new technology, because the one that's being used commercially now is kind of nasty and involves chlorine. So that's a good place for research on battery materials. Well, if we don't switch to new materials, what else can we do? There are lots of ways that we could use less material per battery. There are many ways that we could actually have vehicles that did have sufficient range, but use less material. My personal favorite is plug-in hybrids, which use a smaller EV battery, but also have a backup internal combustion engine to, if the electric range is exceeded, and to recharge the electric vehicle battery if the charge got down too low. And this enables a battery a factor of something like 5 smaller, but with as larger range on the vehicle as you want, without having to have a very large battery that uses a lot of material and is very heavy. The supplementary fuel doesn't have to be petroleum. And one thing that has shown up recently in the Chicago area, where it got to be 12 below 0 Fahrenheit last week for several days, electric vehicle charging in cold weather is an issue if you don't have home charging. And that issue really came home to roost this week. There are also fuel cell vehicles that would use smaller batteries. And a very interesting idea that's being demonstrated in several places is in-road charging. There's a small battery that's on board your car, and if you drive on one of the major highways that's got charging in the highway, your vehicle is charged as you drive along, and so you don't need to have been carrying around 1,000 pounds of batteries, but you can get anywhere that highway goes on electricity. Another interesting idea is battery swapping, which in which you have a small battery, and you, instead of going to a gas station, you go to a battery swapping station to switch batteries when you're low. There are pros and cons of that, and it's not even clear that it actually will save material, but it's worth looking at. And another idea that is based on something that's actually commercial at this point is it's possible to have a small battery for every day. And if you have to go on a long trip, you can rent either a higher capacity battery or add on modules for the battery that you already have. And there, of course, are lots of ways that you can do car or ride sharing. I have been concentrating on ways that we could use batteries but not have to change our lifestyles at all. So Toyota did a little analysis where they said, okay, we have enough battery material for one battery electric vehicle. How can we reduce carbon emissions most with that material? And what they did was they postulated several different fleets, the most interesting of which was 80 out of the 100 vehicles that there would be 84 HEVs and 16 ICEs. And this would use the same amount of material as one battery electric vehicle, or 6 PHEVs and the rest ICEs. And they assumed that all of these 100 vehicles in these 4 example fleets traveled 13,500 miles and looked at what the emissions would be from these vehicles. And lo and behold, the HEVs had the lowest total emissions. You can see there's a little cheat on the graph in that it doesn't go down to 0, but you really couldn't see the difference between the electric options without expanding the scale. And I looked at this study and it made me think. And the trick on it is that they've assumed that all of the vehicles travel the same distance. If you relax that assumption and simplify, because let's face it, the BEV really didn't have a prayer in their study. So if you look at a simpler example with 20 cars, and one fleet is all HEVs, the other fleet is all ICEs plus 1 PHEV, and assume that this fleet now has to travel 300,000 miles. What happens if you enable the different vehicles to go different distances? So that's the graph on the right. The left is the Argonne numbers that we used as inputs to this, which are somewhat more pessimistic for the electric vehicles than the Toyota scenario. And what you see is that once that one PHEV can go a significant fraction of the miles, it actually can reduce the emissions way below the emissions from the fleet that has the HEVs in it. So what that means is that if you have a fleet of vehicles and they're not all going the same distance, you can in fact reduce your total emissions way below what they would have been from that optimistic HEV fleet that Toyota was proposing. So in fact, it should be possible to reduce fleet emissions either from your fleet if you are an owner of a commercial vehicle fleet or a taxi fleet or whatever, by appropriate use of plug-in hybrids. So I think that is an idea that needs to be expanded on and thought through, which basically gets me to the end here. The idea is that rapid growth of demand for battery materials could lead to battery material shortfalls. Recycling isn't gonna solve the problem until growth stops. We can use some alternative materials, and that'll help. But we can also get electrification with reduced material use if we are careful in how we allocate the material and use considered technologies with smaller batteries. And these smaller batteries can be used on high mileage routes, and we can further minimize the CO2 emissions that way. So we can come up with ways to use less materials, and that will also reduce all of the impacts of electrification. And with that, I want to thank the people who invited me, and also my postdoc, Jingy, who did a lot of the calculations, Aramco Americas, which funded some of the work, Circular Energy Storage for their data and their help, and also the U.S. Department of Energy's Vehicle Technologies Office for their continued support. And with that, I'm happy to take some questions.
Thank you so much for that, Dr. Gaines. As with all the talks, we're likely going to have lots of questions from the audience, and I can see that we have received some questions already. So I will move straight on to the Q&A. So the first question that we've got is, do electric vehicles really reduce CO2 emissions?
Well, as I showed, the production of the electric vehicle is probably somewhat more CO2 intensive than production of a conventional vehicle, but the operation of the internal combustion engine is very carbon intensive. And so once you start driving your vehicle around, even if the electricity is produced in a not very clean way, that deficit in carbon emissions is quickly paid back.
Perfect. Thank you for clarifying that. Another question we've received, are life cycle costs of electric vehicles higher than the conventional ICE vehicles?
There certainly are some very expensive electric vehicles out there. There's no particular reason that an electric vehicle needs to be much more expensive in its first cost than a conventional vehicle. And there are currently many electric vehicles that are less expensive than the average price of a vehicle in the US. But the real key to this is the fuel cost, especially if you drive a lot. It's way, way cheaper to fill up your battery with electricity than it is to fill up your tank with gasoline. And so the fuel costs of an electric vehicle are much lower, and also the maintenance costs are much lower as well, because you don't have an engine, you don't have various parts that need to get maintained. So you don't, for instance, you might need an oil change or whatever for an electric vehicle. So the maintenance costs are much lower as well as the fuel costs. So the life cycle cost of an electric vehicle is much lower.
Definitely something to consider there. So another question that we've got, what about environmental impacts of making these batteries?
The environmental impacts of the batteries are in general lower than the environmental impacts. Let me rephrase that. Life cycle impacts of an electric vehicle when it's recycled will be lower than the life cycle environmental impacts of an ICE that's recycled. Does that make sense?
Thank you for the clarification on that one. And I think we've got time for one more question before we will have to sign off. So the last one we're going to take, when can we expect to have a circular economy for batteries?
Well, there are two issues with that. One is we really haven't had the growth flatten out yet. And so we're not going to be able to get enough material back from batteries until we're only using as many as we are coming back. So that is probably not going to be for 20 or 30 years. The other thing is we're not going to be circular if the battery material keeps changing. If we're switching from NMC batteries to lithium iron phosphate batteries, getting NMC batteries back isn't going to make us circular, because that's not what we're going to need the materials for. So having a circular battery economy may be a long time coming, unfortunately.
Definitely plenty for us to think about there. Thank you so much for your talk, Dr. Gaines. Unfortunately, that's everything that we have time for today. Any questions that we didn't have time to get to will be sent to the speaker after the event. So that's it for this year's Advances in Battery Research Symposium. As mentioned throughout the day, all of the talks from today's event will be made available to view on demand for the next 30 days. You can access all of the talks via the same link that you used to access them today, and we'll be sure to pass on any further questions you submit through the system to the relevant speaker. That just leaves me to say thank you again for attending, and we'll see you again at our next online symposium, Cell and Gene Therapy. Goodbye.